Imagine a world where oceans exist without sunlight, tucked away beneath kilometers of ice. This is not fiction. Beneath the icy surfaces of Jupiter's moon Europa and Saturn's moon Enceladus, vast liquid oceans lie in perpetual darkness, warmed not by the sun, but by the subtle gravitational tug of giant planets. These are the alien oceans, and they may be among the most promising habitats for life beyond Earth. Europa is a frozen sphere crisscrossed with cracks, ridges, and chaotic terrains. Beneath its icy shell, scientists believe a global ocean of salty water stretches perhaps 100 kilometers deep, far deeper than Earth's oceans. Evidence comes from NASA's Galileo mission and Hubble observations, which hint at the motion of ice and possible plumes venting from the interior. Magnetic field measurements reveal a conducting layer, consistent with a salty ocean, and surface ice patterns suggest dynamic interactions with the water below. Enceladus, smaller but equally remarkable, actively ejects its ocean into space. Cassini spacecraft discovered geysers of water vapor, ice particles, salts, and organic molecules shooting hundreds of kilometers above the South Pole. These plumes provide a direct way to sample the ocean and study its chemistry. Scientists detect hydrothermal signatures, indicating water-rock interactions that on Earth sustain diverse ecosystems. These oceans are heated not by sunlight, but by tidal forces. As Europa and Enceladus orbit their giant planets, gravitational flexing generates friction in their interiors, keeping water liquid under immense pressure. This tidal heating maintains dynamic environments, potentially capable of sustaining life. The ice itself is not a static barrier. It can fracture, shift, and even allow nutrients and oxidants from the surface to mix with the ocean below, creating a dynamic chemical environment. Life on these moons would not rely on sunlight, but on chemical energy, heat, and nutrient fluxes from water-rock interactions. On Earth, ecosystems thrive in complete darkness near hydrothermal vents, converting chemical energy into life-sustaining processes. If similar processes occur beneath Europa or Enceladus, we could witness forms of life radically different from anything on our planet. Microbial colonies could form around energy hotspots, while more complex organisms might exploit chemical gradients, forming ecosystems invisible from the surface. The ice layers may also trap and circulate gases, such as oxygen and carbon dioxide, formed by radiation-driven reactions in the surface ice. These chemicals could eventually migrate down to the ocean, providing additional energy sources. Seasonal or periodic changes in orbital dynamics could create pulses of energy and nutrients, offering temporal niches where life could flourish intermittently. Future missions aim to probe these oceans. Ice-penetrating radar, plume analysis, and spectrometry will help determine ocean depth, composition, and habitability. These investigations are not just technical, they are philosophical. By studying alien oceans, we confront profound questions. How flexible is life? How does it adapt to environments radically different from Earth? And most importantly, are we ready to recognize life in forms we have never seen? In this series, we will explore how alien oceans function, how they could support life, and what this means for humanity's search for life beyond Earth. From the icy surfaces and hidden currents to potential ecosystems fueled by chemical energy, the story of Europa and Enceladus reminds us that the universe is far richer and stranger than our everyday experience suggests. These oceans beneath the ice are not merely scientific curiosities, they are windows into the possibilities of life itself. Europa's icy crust is far from uniform. Some regions may be tens of kilometers thick, while others could be just a few kilometers, forming thin zones and cracks where the ocean interacts directly with the ice above. These surface features, such as linea, long, dark streaks stretching thousands of kilometers, reveal tectonic activity. The chaotic terrains, where ice appears broken and rotated, suggest regions of ice that have melted and refrozen, hinting at dynamic interactions between the ice shell and the subsurface ocean. Beneath this crust lies a salty, global ocean potentially containing more water than all of Earth's oceans combined. Magnetic field measurements from the Galileo spacecraft suggest a conducting layer consistent with a salty ocean. Salts like magnesium sulfate and sodium chloride, dissolved in water, not only lower the freezing point, but also provide a medium for chemical reactions necessary for life. The ocean may also contain other dissolved minerals leached from Europa's rocky mantle, providing nutrients and energy sources. Tidal heating is the primary driver that keeps Europa's ocean liquid. Gravitational interactions with Jupiter and its neighboring moons create constant flexing of the ice shell and the interior, generating frictional heat. This heating may create convection currents in the ocean, circulate nutrients, and sustain hydrothermal systems at the seafloor. Hydrothermal vents could provide the energy gradients needed for life, similar to the ecosystems found around Earth's deep-sea vents. Radiation from Jupiter's intense magnetic field constantly bombards Europa's surface, breaking water molecules into oxygen and hydrogen. Some oxygen could slowly migrate through cracks into the ocean below, offering additional chemical energy. This process creates the potential for chemical disequilibrium, a necessary condition for metabolism. Life, if present, could exploit these redox reactions, converting chemical energy into growth and reproduction. Hubble Space Telescope observations hint at occasional water plumes erupting from Europa's surface, which, if confirmed, offer a unique window into the composition of the ocean below. These plumes could contain salts, organics, and other materials that provide clues about habitability. Even tiny amounts of material escaping into space allow scientists to sample the ocean remotely without the need to drill through kilometers of ice. Modeling Europa's ocean is complex. Ocean circulation, ice dynamics, and chemical fluxes interact to create a three-dimensional, constantly changing environment. Scientists use simulations to predict where life is most likely to exist, identifying potential habitable niches near hydrothermal vents, ice-water interfaces, or regions with concentrated oxidants. The potential for life in such an environment challenges traditional definitions. Organisms may be microscopic, slowly metabolizing, or forming colonies adapted to extreme pressure, low temperature, and darkness. Yet even the tiniest life forms would reshape our understanding of biology, proving that life can thrive independently of sunlight and oxygen-rich atmospheres. Europa is not just a frozen moon. It is a laboratory for extreme biology, a place where ice, rock, and chemical energy converge to create possibilities for life. Studying this world will not only help answer whether we are alone, but also reveal the remarkable adaptability of life in the universe. Its hidden ocean represents one of the most compelling frontiers in the search for extraterrestrial life. Enceladus, Saturn's small but remarkable moon, presents one of the most accessible windows into alien oceans. Unlike Europa, whose ice shell may be tens of kilometers thick, Enceladus's subsurface ocean interacts with the surface more dynamically. The Cassini spacecraft revealed active plumes erupting from the South Polar region, fountains of water vapor, ice grains, salts, and complex organic molecules shooting hundreds of kilometers into space. These plumes allow scientists to directly sample ocean material, bypassing the need to drill through thick ice, making Enceladus an unparalleled natural laboratory for studying extraterrestrial habitability. Tidal heating drives Enceladus's activity. As the moon orbits Saturn, gravitational forces flex its interior, generating frictional heat. This process maintains a liquid ocean beneath the ice. Concentrated near the South Pole, the tiger stripe fractures. Deep fissures along which the plumes erupt indicate regions of intense thermal activity, likely above localized hydrothermal hotspots on the ocean floor. These hot zones create chemical gradients, offering energy sources potentially exploitable by life. Chemical analysis of plume material shows the presence of molecular hydrogen H, carbon dioxide CO, salts, and simple organic molecules such as methane. Molecular hydrogen is particularly significant because it is a potent energy source for chemosynthetic life, as demonstrated by Earth's hydrothermal vent ecosystems. Hydrothermal vents on Enceladus could create microenvironments where microbial metabolism converts hydrogen and other molecules into usable energy. In essence, the ocean could host localized oases of chemical energy. Hidden beneath kilometers of ice, the ocean's alkaline pH further enhances its habitability. Laboratory simulations suggest that such conditions are conducive to microbial growth, as enzymes and metabolic reactions can function efficiently at these chemical parameters. Moreover, the presence of silica nanoparticles and plume particles indicates ongoing water-rock interactions, supporting the hypothesis that the seafloor provides mineral nutrients necessary for sustaining life. Enceladus's plumes also provide a unique opportunity to study potential biosignatures. Variations in isotopic ratios, concentrations of organic compounds, and chemical disequilibria could indicate biological activity. Detecting such patterns would not only suggest the presence of life, but also help characterize the types of metabolisms that might exist in alien oceans. The dynamics of the ice shell play a critical role. Enceladus's thin, fractured ice allows continuous exchange between ocean and surface. Radiation on the surface may generate oxidants, which then migrate downward, mixing with reductants from the rocky core. This chemical flux could sustain life in a manner analogous to redox-driven ecosystems on Earth. Life on Enceladus, if it exists, may not resemble earthly organisms in size, speed, or complexity. It could consist of microbial mats, modal microorganisms, or even small multicellular life adapted to high pressure, low temperatures, and perpetual darkness. Yet even minimal life forms would profoundly alter our understanding of biology, demonstrating that life can flourish independently of sunlight and the planetary surface environment. Enceladus represents a dynamic, interactive system where energy, chemistry, and geology converge to create habitable niches. Its ocean is not static, but continuously evolving, offering scientists a unique opportunity to study the processes that make life possible in extreme, hidden worlds for humanity. Exploring Enceladus brings us closer to answering a fundamental question: is life a universal phenomenon, capable of emerging and thriving beyond Earth? To imagine life in alien oceans, we turn to Earth's extremophiles, organisms thriving in environments previously thought completely inhospitable. Deep-sea hydrothermal vents, for instance, support complex ecosystems in total darkness, where sunlight never penetrates. Here, microbes convert chemical energy from hydrogen sulfide and methane into biomass, forming the foundation of food webs that sustain clams, worms, and other invertebrates. These chemosynthetic systems prove that life does not require sunlight, and instead can rely on chemical gradients and mineral energy sources. In Antarctica, subglacial lakes such as Lake Vostok or Lake Whillans harbor microbial life trapped beneath kilometers of ice. These organisms survive in complete darkness, under immense pressure, and with limited nutrients. Some metabolize extremely slowly, essentially in suspended animation, yet maintain active cellular processes for thousands of years. Such life demonstrates that biological processes can persist in isolation and under extreme environmental stress. Extremophiles also thrive in extreme pH, salinity, and temperature. Thermophiles flourish near boiling hydrothermal vents, acidophiles tolerate pH near zero, and halophiles survive in briny conditions hostile to most other organisms. Their biochemical flexibility, specialized enzymes, membranes, and metabolic pathways provides a roadmap for what alien life in icy moons might look like. The lessons from Earth extend to energy sources and ecosystems. Hydrothermal systems create localized chemical energy hotspots, just as Europa or Enceladus might have beneath their ice. Redox reactions, where electrons are exchanged between molecules, provide metabolic energy in the absence of sunlight. Life can exploit these gradients, forming ecosystems around chemical fluxes, with possible trophic hierarchies and nutrient cycles. Even in a nutrient-poor environment, biological communities can persist by efficiently recycling matter and energy. Extremophiles also help define potential biosignatures for alien oceans. Isotopic fractionation, unusual molecular structures, or mineral formations influenced by microbial activity could indicate life even without direct observation. For example, methane with a distinct isotopic signature at Enceladus's plumes could point to biological production rather than abiotic chemistry. Understanding how extremophiles function on Earth allows scientists to interpret subtle chemical and physical signals in extraterrestrial oceans. Furthermore, Earth's extremophiles highlight the adaptability and resilience of life. They show that biological activity can persist under high pressure, low temperatures, and complete darkness, conditions common in subsurface oceans of icy moons. Life may be slow-growing, microscopic, and highly specialized, but it can nonetheless sustain itself over geologic timescales. Studying these organisms also informs our mission design for detecting life. Instruments must be sensitive to chemical anomalies, isotopic ratios, and organic compounds. Subtle variations over time could indicate active metabolisms, just as slow metabolic processes in extremophiles leave measurable chemical footprints. The extremophiles of Earth therefore serve as both proof of concept and inspiration. If life can persist beneath kilometers of ice or deep within the crust, there is no fundamental reason why similar processes could not occur in the hidden oceans of Europa or Enceladus. These ecosystems guide our expectations, shape our scientific models, and fuel our imagination, providing a template for what alien life might look like and how we might find it. Life in darkness is possible, and Earth's extremophiles demonstrate that energy, chemistry, and resilience are the universal drivers of habitability, a lesson we carry to the frozen oceans of other worlds. In the absence of sunlight, life in alien oceans must rely on chemical energy to survive. This energy comes from redox reactions, exchanges of electrons between molecules, which drive metabolism. On Earth, chemosynthetic organisms near hydrothermal vents oxidize hydrogen, methane, or sulfide to generate energy, forming the base of an ecosystem in total darkness. Similar processes could occur in the subsurface oceans of Europa and Enceladus. For example, on Enceladus, water-rock interactions within the Moon's rocky core can produce molecular hydrogen H. This hydrogen, when combined with carbon dioxide, creates a potential energy source for microorganisms. Hydrothermal vent systems on Earth demonstrate that such chemical energy can support diverse and complex communities even without sunlight. In the alien oceans, microbial life might exploit these chemical gradients, forming localized hotspots of biological activity. Europa's ocean may also support chemical energy pathways. The ice surface is bombarded by Jupiter's radiation, breaking apart water molecules and creating oxidants, such as oxygen and hydrogen peroxide. Over time, these oxidants could migrate downward through cracks in the ice, reaching the ocean and interacting with reduced compounds from the rocky seafloor. This creates chemical disequilibrium, which is essential for sustaining metabolism. Life could use these redox gradients as a source of energy, similar to how Earth organisms exploit oxygen sulfide reactions. The chemical environment may also allow for alternative biochemistries, while Earth life relies on carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Life elsewhere could incorporate other elements or use different solvents. For instance, ammonia or methane could serve as cryogenic solvents, broadening the conditions under which life could exist. High pressure, low temperature environments, once thought inhospitable, may actually favor unique adaptations, allowing enzymes and cell membranes to function efficiently. Potential ecosystems could vary in complexity. Simple microbial mats may dominate regions near energy-rich vents, while more complex organisms could exploit gradients in temperature, chemical concentration, or nutrient availability. Food webs may be short and highly efficient, recycling energy with minimal loss, or more diverse if hydrothermal activity provides sufficient energy. Seasonal or orbital variations could create temporal niches, where life experiences bursts of activity in response to fluctuating chemical or thermal conditions. Chemical processes also shape biosignatures, indicators of life that spacecraft instruments can detect. These may include unusual isotopic ratios, depletion or accumulation of specific chemicals, or patterns in organic molecules unlikely to occur abiotically in Enceladus's plumes or Europa's ice. Detecting hydrogen depletion, methane anomalies, or complex organics could hint at ongoing biological activity. Scientists design missions to identify these subtle signatures and distinguish them from purely chemical processes. Understanding chemical pathways in alien oceans informs future exploration. By predicting where energy and nutrients concentrate, scientists can focus missions on likely habitable regions. Instruments such as mass spectrometers, spectrophotometers, and ice-penetrating radar are tailored to detect molecular patterns, isotopes, and chemical fluxes that may signal life. Ultimately, chemical pathways define the possibilities for life beneath the ice. Even without sunlight, these oceans could harbor ecosystems sustained entirely by the hidden energy of their worlds, offering a profound example of how life adapts to extreme environments and broadening our understanding of where life can exist in the universe. Detecting life beneath the ice of Europa and Enceladus is one of the most ambitious challenges in modern science. Direct access to these oceans is currently impractical. Europa's ice shell may be tens of kilometers thick, and even Enceladus, with its thinner crust, presents significant technological barriers. Instead, scientists focus on indirect methods, analyzing plumes, surface ice, and chemical exchanges to infer the presence of life. Enceladus offers a unique advantage. Its plumes eject water, salts, organic molecules, and potential biosignatures directly into space. Instruments aboard the Cassini spacecraft detected molecular hydrogen, simple organics, and silicate particles, suggesting active hydrothermal chemistry on the ocean floor. These measurements allow scientists to study the ocean's composition without drilling through the ice, providing invaluable clues about habitability. Europa, though less active, presents potential plumes and surface exchanges. The Hubble Space Telescope has observed hints of transient water vapor emissions, which could be sampled by flyby missions. Even if plumes are rare, cracks and ridges in the ice shell may transport chemicals and oxidants from the surface to the ocean below, creating detectable chemical gradients. These gradients are key. Life requires energy, and these disequilibria provide potential metabolic opportunities for hypothetical organisms. Biosignatures are central to detecting life. Scientists look for organic molecules such as amino acids, lipids, or hydrocarbons, isotopic ratios that indicate biological fractionation, chemical anomalies like hydrogen depletion or oxidant consumption, mineral structures shaped by biological activity. Detecting biosignatures is challenging because many chemical features can also form abiotically. Methane, for instance, can be produced by hydrothermal reactions or radiolysis. Therefore, scientists search for patterns and combinations of signals that are statistically unlikely without biological processes. Repeated sampling, temporal monitoring, and multi-instrument analysis increase confidence in identifying potential life. Upcoming missions are designed to maximize detection potential. NASA's Europa Clipper will conduct multiple flybys of Europa, mapping the ice shell, analyzing surface composition, and searching for plumes. Proposed missions like the Enceladus Life Finder aim to sample the Moon's plumes more directly, with instruments capable of detecting organic molecules and isotopic signatures at unprecedented sensitivity. In the future, landers or autonomous submersibles may probe the ice and oceans directly. Although these missions remain technologically challenging, understanding alien oceans also informs mission planning. Extremophiles on Earth demonstrate that life can survive in low energy, high pressure, and dark environments. This guides instrument design. Spacecraft must be sensitive to chemical disequilibria, subtle organic compounds, and isotopic ratios. Even tiny deviations from expected abiotic chemistry could indicate life. Beyond technical challenges, the search for life beneath the ice carries profound philosophical implications. Confirming extraterrestrial life would demonstrate that biology is a universal phenomenon, capable of emerging in environments radically different from Earth. It would reshape our understanding of evolution, adaptation, and the potential diversity of life in the cosmos. The oceans of Europa and Enceladus are not static. They are dynamic, chemically active, and potentially biologically productive. By studying plumes, surface ice, and chemical fluxes, we may uncover ecosystems thriving in the dark, providing a glimpse of life beyond Earth. These missions bridge the gap between imagination and reality, transforming alien oceans from theoretical possibilities into tangible targets in humanity's quest to understand life in the universe. The discovery of alien oceans beneath the ice of Europa and Enceladus is more than a scientific curiosity. It reshapes our understanding of where life can exist and what forms it might take. These oceans, isolated from sunlight, heated by tidal forces, and chemically active, represent environments profoundly different from Earth, yet potentially capable of sustaining life. Understanding them challenges the traditional notion that life requires a surface, atmosphere, or direct sunlight. If life is found, even at a microbial level, it would demonstrate that biology is not unique to Earth. It would confirm that life can arise in diverse chemical and physical environments, and that the universe may host numerous forms of life beyond our imagination. This realization would spark a profound cultural and philosophical shift, emphasizing the universality and adaptability of biology. Humanity would no longer view itself as the sole arbiter of life, but as one participant in a broader cosmic network. Exploration of alien oceans also drives technological innovation. Missions like Europa Clipper, future landers, and proposed submersibles push the boundaries of robotics, autonomous navigation, ice-penetrating technology, and in-situ chemical analysis. Developing instruments sensitive enough to detect subtle biosignatures in extreme environments requires collaboration between engineers, chemists, astrobiologists, and planetary scientists. These technologies could have spin-off benefits on Earth. From deep-sea exploration to environmental monitoring, the presence of subsurface oceans also informs planetary protection protocols. Any mission must prevent contamination, ensuring that Earth microbes do not compromise potential extraterrestrial ecosystems. This adds complexity to spacecraft design and mission planning, emphasizing ethical considerations alongside scientific goals. Humanity faces a responsibility to explore thoughtfully, preserving alien oceans as pristine laboratories for understanding life. Beyond the scientific and technical aspects, alien oceans reshape our approach to habitability. They demonstrate that energy, chemistry, and dynamic environmental interactions, rather than surface conditions alone, determine the potential for life. The study of Europa and Enceladus encourages scientists to expand the search for life to other icy moons, dwarf planets, and even exoplanets with subsurface oceans, broadening the scope of astrobiology. Moreover, these discoveries inspire public imagination and interdisciplinary collaboration. Science fiction, once a source of speculation, now intersects with scientific reality. Concepts like underwater alien ecosystems, life in darkness, and ecosystems driven by chemical energy become plausible scenarios, fueling curiosity, education, and engagement with STEM fields. Students, educators, and the public gain a tangible connection to the frontiers of space exploration, making alien oceans a shared point of fascination. Finally, the exploration of alien oceans reminds us of humanity's place in the cosmos. Beneath the ice of distant moons lies a universe of possibilities, hidden worlds with energy, chemistry, and perhaps life, evolving silently and independently of Earth. These discoveries challenge us to reconsider our assumptions about life, to develop new technologies, and to act responsibly as we reach beyond our planet. In conclusion, the alien oceans of Europa and Enceladus are not merely scientific targets. They are windows into the potential diversity of life in the universe. By studying their chemistry, energy flows, and geological dynamics, we prepare to answer one of humanity's most profound questions. Are we alone, The pursuit of this knowledge pushes the limits of science, engineering, and imagination, reminding us that the universe is far more complex, mysterious, and inspiring than we ever imagined. These hidden oceans beneath the ice invite us to explore, to learn, and to marvel at the extraordinary possibilities of life beyond our world.